image, which I am showing now, which instances require a Slack variable for SVM. So if you're having some trouble even answering this question or knowing where to start here, imagine that you have this feature space, like some training data, right? And you are trying to classify if you have a plus or a minus, right? What the question is asking you is, given this plot of your feature space, which of these instances for support vector machines would require a Slack or a zeta variable? Another question you may have before you can answer this is, what in the world is a Slack or a zeta variable, right? And simply put, support vector machines is trying to maximize the margin or the decision, the margin of the decision boundary, right? So if you think of your decision boundary as these minuses that go across your data, you will notice that you have in the training data itself 2 misclassified items. And the reason that is because some data, some training data that you get is just not linearly separable, right? So that means you just can't really draw a nice straight line and get all the pluses on one side and all the minuses on the other. And the support vector machine algorithm needs to be able to maximize the size of this margin while at the same time minimizing classification errors. So in order to do that, you have to have this metric, something to measure, like how many items were misclassified, how bad were they misclassified. And the way that the algorithm itself kind of works is it says, oh, I will take the distance from, say, this misclassified plus over here to the decision boundary, and I will create this thing called a Slack variable that kind of accounts for that, right? And the same thing would happen for A. So A and D would be your zeta or your Slack variables. Hello, this is Dr. Drew from the Data Science at SMU program at SMU. I'm teaching a class on Machine Learning 1. Would you be willing to answer a few questions for our class tonight? ChatGPT says, of course, I'd be happy to answer any questions you have about machine learning. Just let me know what you'd like to know. All right. Well, we're talking about support vector machines. Can you quickly summarize the SVM algorithm? ChatGPT says support vector machines is a supervised learning machine learning algorithm that can be used for classification and regression tasks. The main idea behind SVM is to find a hyperplane, a line or a plane in a high dimensional space that best separates the data into classes while maximizing the margin between the hyperplane and the closest data point, which are called support vectors. These support vectors define the decision boundary, which is used to make predictions for new data points. SVM algorithms use a technique called the kernel trick to transform input data into a higher dimensional space, making it possible to find a nonlinear decision boundary. The choice of the kernel and parameters used in the algorithm can have a significant impact on the performance of the model. Okay, well, we were just talking about Slack variables, right? So can you tell us about Slack variables in SVM? Slack variables, also known as soft margin, are a key concept in support vector machines. They are used to allow some misclassifications in training data, which can help the algorithm avoid overfitting and improve the generalization performance of the model. In a hard margin SVM, the goal is to find a hyperplane that separates the data into classes with no misclassifications. However, in real-world data, it is often not possible to find a perfect hyperplane that separates the data without errors. In these cases, Slack variables are introduced to relax the constraint of having no misclassifications. Let's refer back to this real quick and remind ourselves, what in the world are we actually practically talking about? We're trying to classify, low, high, false, true, plus and minus, right? Our data is not linearly separable because we cannot draw a linear line to get all the pluses on one side and all the minuses on the other. So we create a Slack variable to account in the algorithm itself for how many misclassified items that we have, how poorly are they classified. Let's see what else it has to say. Slack variables are non-negative variables that are associated with each training example. So again, we go back. If each of these instances that we're looking at in this image, by the way, this is completely unplanned and so far working out pretty well, I would add. Each one of these would be a training record, right? They're a literal record in your training data, labeled as a plus, labeled as a minus, right? And we have two misclassified. They are linearly separable because we cannot draw a straight line to get all the minuses on one side, all the pluses on the other. The objective of SVM optimization problem is then to find the hyperplane that maximizes the margin while allowing for some misclassifications controlled by a parameter called C. Does anybody know what C stands for? You probably wouldn't unless you looked at the parameters for support vector machines, but C stands for cost, as in the cost of errors, right? So what C is asking you when you are tuning your model, C is saying, hey, how important are misclassified items to you? And really the answer to that is very subjective and it depends problem by problem. So for example, if you were building a machine learning model to tell somebody that whether or not they had a terminal illness, a misclassified item would be like very, very bad, right? You definitely don't want to tell somebody, hey, you have a terminal illness when you don't have a terminal illness. So the cost of errors in a case like that, really, really high. If you're talking about marketing mail pieces and you already market to 80% of the households in the United States, which shockingly is pretty common for like large banks and places like that, maybe the cost of misclassified items is much lower, right, than an algorithm for a heat-seeking missile. There's just differences in how important the cost of errors are. So yeah.
What would be considered a high C and a low C? I see the default a lot of people use is just 1, but I'm not really sure how that is.
So that's not easy to answer because it's going to be driven, I think, by the data type that they've used to define it. So you could say 5 is higher than 1. 1 would be like there's no cost for errors, but it is going to influence the type of decision boundary that you get. And I have an example of that I'll show you in a second. But the highest is probably going to be int32.max or int64.max, depending on how. You'd have to look in the Sklearn source code, which you can actually do if you're interested in it, and see how it's been coded. But the objective of SVM optimization problem is to then find the hyperplane that maximizes the margin while allowing for some misclassifications controlled by the parameter C. The larger the value of C, the smaller the slack variables are allowed to be, and the harder the margin constraints become, leading to a model that is more likely to overfit to your training data, right? By introducing slack variables, SVM algorithms can handle non-linearly separable data and noisy data and can produce more robust models that generalize well to unseen data. Okay, so let's take a break. Thank you. We will be back in a minute. Okay, so this was a presentation that I normally go through for each one of my classes every semester to talk a little bit about support vector machines. Can everybody see this presentation okay? Okay, awesome. All right, so this was a trick question. I'll give you the answer to save a little time. The question was, which one of these lines is the best line to separate the circle or the square? Well, the answer is, if you were Vladimir Vapnik back in like the 1940s, you would have said none of these lines are the best answer. The best answer is the line that maximizes or creates the optimal separating hyperplane, right? So all he's saying is, look, you need to draw a line to separate your two classes that has as much margin on each side of the decision boundary as possible. The theory behind that being you probably haven't seen all the cases of the data that your model will predict at some point out in the future, right? So why not make your model as flexible and as general as possible by maximizing this margin? Then hopefully, say if you had a bunch of circles that kind of fall in here that were never seen by your training data, your model should still kind of get it right. This is okay, pretty simple when you're talking about like a two-dimensional problem, right? But in actuality, these hyperplanes, they're a geometric concept, right? And in many cases, we're doing a multi-decision hyperplane or a multi-dimensional hyperspace. And if you've ever looked at like graphs of multi-dimensional data, they start to go from like your typical two feature graph, and then you have the z-axis that comes off the back. Well, think if you draw 1,000 more of those axes, all from a center point of origin, you start to get this weird looking like circle shape, right? And this is probably pretty naive, but I kind of think of it like imagine if you had like a clear fish tank full of gel, these little dots in there. And you're taking like a string or some sort of plastic and trying to wrap a circle or wrap a ribbon around each one of the different colors. Sometimes you can do it, like in this example on the left. Sometimes you can't. You have like a few misclassified items, right? And we are talking all about these slack variables and how they work. What SVM tries to do is it tries to optimize the margin, right? And so the objective function is usually is going to be equal to 1 over the margin. However, there's, like we said, the certain instances where the classes aren't linearly separable. And so we need to add a way to account for that, which is kind of the second part of the objective function that we see over here on the right with the cost of errors, and then summarizing all these zeta or slack variables. So this example, circles and squares, and we have, one misclassified circle, and then we have one misclassified square. And so we're getting a zeta or a slack variable for each one of those. And basically, we want an objective function that maximizes the margin and minimizes the training errors. And as we increase C, we're saying we care a lot about classification errors. I know that it was explained to us by ChatGPT a little bit how C influences the decision boundary. But I think this particular graphic might give us a little bit better visual understanding of how this might work. So let's say you set C equal to 1. A low cost is going to give you a wider margin, which in theory generalizes better to your training data, right? But let's say you increase C to like 5 or 10 or 100, and it has to redraw the line. What it's going to do is it's going to try to redraw this line in such a way that you minimize as many of your training errors as possible. So if you look at the green line, you have 2 misclassified items, but if you redraw that using a lower cost, you might move the misclassified square over to the correct side of the decision boundary. You can't quite get to the circle, right? And but you see the effect that has, right? So notice the margin, the dashed lines, when you moved over to your higher cost, they have to be much smaller in order to get that one additional training record to the correct side of the decision boundary. So Kendall asked, does high C mean a risk of overfitting potentially? And it most certainly does, right? As far as I know, we do not have like a really good idea of what the value of C could be. It tends to vary from problem to problem and data set to data set. So my best guidance for you in this class on any type of hyperparameters, like what should the value be, I would say you need to do cross-validation. And so when we do cross-validation, we would test and we would say, well, if we do tenfold cross-validation with a cost of 1, and then we do it with a cost of 5, which one has improved the metric that we're looking at for our cross-validation, right? But that's an interesting question, and I think it might be worth worth trying out. So how do we choose the best parameter value for C? Sorry, my keyboard is crooked here. For C when using SVM. Okay, so this gives us the first option that I talked about. And it says, hey, you should use a grid search with cross-validation. One common method is to perform a grid search over a range of values for C, and then evaluate the model performance using cross-validation. The value of C that results in the best performance on the validation set is selected as the optimal value. Random search with cross-validation. So this would be the same option. I'm not going to read all this. I'll just quickly explain it. You're welcome to read it if you want. But random search with cross-validation says, hey, I have so much data to go through. Perhaps I can speed up my cross-validation doing it in a randomized fashion. So you're giving up a little bit of accuracy here, but in exchange, you're getting much faster performance going through your cross-validation. You can also do model selection techniques such as Bayesian optimization or genetic algorithms can also be used to find optimal value for C. These methods are more computationally intensive than the previous methods, but provide better results in some cases. In general, the best value for C will depend on the specific problem and the data being used. That's exactly what I said. I'm waiting for it to disagree with me, and if it does, that's fine. I will learn because it is probably right, but maybe not. Who knows? It's recommended to try multiple methods and compare the results to find the best value for C for a particular problem. So at this point, I have to ask everyone, because I mean, we're going into our first real big lecture about like how do you do machine learning tonight. How many people are familiar with what a grid search even is? Got one. Okay, not very many. How many people feel like they're very familiar with what cross-validation is? One, two, three, a couple of people, right? Okay, so I'm going to break this down in a nutshell. Cross-validation, right? You need some testing and some training data, right? So in the simplest case, you maybe have one test fold, which is a random selection of say 10% of your data, right? So 10% of your data for test, 90% of your data for train, and then you train your model on your training data, you test your data on the 10% of test records, and you score yourself. You say, how many pluses did I get correct? How many minuses did I get correct, right? If you do that, say 10 times, and you keep using unused records. So think of it this way. You take your whole data set and you randomly shuffle it, right? And then you divide it into 10% segments. So if you did 10-fold cross-validation, fold number 1 would become your test data. Folds number 2 through 10 would become your training data. And then fold number 2 in your second iteration would be set aside. And then fold number 1 and fold number 3 through 10 will become your training data. And you repeat that process over and over and over again until every single record in your data set has been tested, right? And every single record in your data set has been included as training data. And what does that do? Somebody help me out with that, so I don't have to talk so much. Well, why would we go through this process of building 10 different models? Sounds like a lot of time.
It kind of helps so you don't get lucky on one of your splits, and also helps account for any like groups of outliers.
Yeah, I would totally agree with that. And so I will expand on that. Lucky would mean, let's say by random selection, you just happen to get the 10%, of your randomly selected records that your model is just like, oh, these are easy, got it in the bag. And so your model comes out scoring like 95%. But if you repeated that 9 more times, all of the other accuracies for those other folds may be like 5%, 10%, 15% lower, right? And so doing this 10 times will give you like a maximum accuracy, a minimum accuracy, and a mean and a median accuracy And you can kind of go to your executive management or the people that you work for and say, here's how I think this model will perform on unseen data, right? So, what's that look like in code? Well, let's ask ChatGPT. Can you show us an example? Get ready to have your mind blown. I just can't even. Okay, so I'm just going to tell you right off the bat, ChatGPT is taking some liberties here and has decided not only to show us cross-validation, but to also include a grid search, which we can talk about. I usually break these two things apart, but in this example, grid search CV function is used to perform grid search over the C and gamma parameters of support vector machines. The grid search uses five-fold cross-validation, and the best parameters are found by evaluating the mean cross-validated accuracy. The best parameters and best score are then printed at the end. So, yeah, we've imported NumPy, we've imported Sklearn data sets, and that's because we want to get the iris data set, it looks like, from sklearn.datasets. And then we're using grid search CV, which means a cross-validated grid search from sklearn.model selection. And then, of course, we're using our support vector classifier from sklearn.svm. So a couple of semantics, and I love that it's following the general sklearn semantics, right? What is X in this instance? Do we know?
Isn't it basically the data set of iris outside the target predictor variable?
That's correct. It is our training data minus the target. Another way to say this would be like iris.data and iris.target, right? So .data is what we're going to fit or train our model on. All of these functions, they're going to have a fit and a predict function. So like support vector machines will have .fit and .predict. Logistic regression will have .fit, .predict. And this makes everything kind of play nicely together because all the estimators in sklearn inherit from this estimator class, right? And there's only like two really concepts you have to know in sklearn, which is you have transformers, which are things that change your data, and you have estimators, which are things that make predictions on your data. So for the most part, that's kind of how the framework works. So here in this particular case, it's showing you you want to do some cross-validated grid search to find what are the best values for cost and what are the best values for gamma using your model in the iris dataset, right? And so the way this works, and you have to be really careful with this because some of these algorithms, especially support vector classifier, the overhead for creating these models can be rather expensive, right? So my point is that if you chose, in this case, they chose to do five-fold cross-validation. But in most cases for our class, we would usually do 10-fold cross-validation unless you have a pretty good reason. But if you did, say, 10-fold cross-validation, and you did a grid search over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 5 and 5. You did a grid search over 5 different possible parameter combinations. I believe, if I'm not mistaken, you would get 5 times 5, 25 different possible combinations of cost and gamma. But you're also doing 10-fold cross-validation, right? So you'd have to do that 10 times for every possible combination, which gives you how many models that you would have to build. $250, right? 25 different combinations, 10 folds for each combination. You'd have to build 250 models. If you have a smaller data set, like if you have 10, 20, 30, 40,000 record data set with only a few columns, maybe that's not a big deal. In other cases, it could be a very big deal. So a lot of times what I recommend is training like one fold of your model, right? To see how long that takes and then kind of approximate, because it will tell you when you do the grid search, it'll tell you doing this many fits for this particular model, right? And you'll know right off the bat, like how many models you have to build, and you can kind of like, back of the napkin figure out, like, is this going to take hours? Is this going to take minutes? Is this going to take weeks? Is this going to take years? Because if it's years or weeks, then you probably need to rethink or reduce the number of parameters that you're testing. Where people really screw up sometimes is they may use the Python range function in here, and they may put in the wrong step. And so it looks like just a little short piece of code, but they end up generating like 200 parameters that they have to test, and they don't realize it. And then they're like, oh, snap. I got to fit 4,000 models. What's crazy is if you're doing something like logistic regression, it still may just rip through them all and you'd be fine. With support vector classifier, you would not be fine. You'd be here for days. Okay, but the rest of this code, the way it works is you create a support vector classifier. In this instance, they've chosen to use the radial basis kernel. There's several kernels that you can choose from. In case you don't know this already, I highly recommend, I do something like SVM, Sklearn. You can see it in my search history. And then I always look for the scikit-learn.org page. And it will show you the documentation for SVC. The way that you read this documentation is there's a parameters section, right? And it shows you, here's all the parameters I can tune. Here's cost. Cost has a default value of 1, but you can put pretty much anything you want in here. You can increase the cost however you want. Here's kernel. The choices are linear, poly, RBF, sigmoid, pre-computed, or callable. And it defaults to the radial basis kernel, right? And then there's all these other different things that you can play around with in terms of parameters. These are all things that you could put in your parameter grid here, right? So you could put those in your parameter grid. So right now there's cost and gamma. So notice at the top we have C, and then we have gamma, right? But you could also add kernel, and you could test all these different kernels. By the way, linear support vector classifier is actually not support vector machines. Like, that means don't use the kernel trick, just use, it's linear regression with an optimized boundary. So keep that in mind. And then, you could play around with the different variables that are available here. The other thing it has is attributes. And this is very important to point out about sklearn. There's a lot of properties or attributes that will not exist on a model until you fit the model. And so what that means is just think about it really basically. If you were doing linear regression, right? You wouldn't have a bias column and an intercept until you fitted the model, until you actually did the matrix multiplication, right? And so any of these kind of properties that don't exist until the fit function is called, they end in an underscore. So that means that you won't have this attribute when you create the SVC object right here, and you have SVC. If you did SVC dot and hit the tab key or whatever, you won't have a class weight or a classes or a dual coef or a fit status or an intercept or a number of features. All these things will not exist until after you call the fit function, which doesn't occur until way down here, right? So, so they're just dynamic properties. And then at the very end, you will also have your attributes. Oh, here we go. Then you'll have your methods, right? And so every single one of these estimators, whether it's a classifier or a regressor, is going to have a fit function. It's going to have a predict function. Most of them will also have predicted probabilities and some other methods in here that you can call or use. And they're usually at the end will be a lot of examples about how to use your different models, right? And so And so in this particular case, this goes through, it performs the grid search by calling grid search.fit. This grid search CV can be used with any estimator. So I would point out that it has passed in the support vector machine classifier that it's created right here. But this could just as easily be LR equals logistic regression. It could be a different model, and you pass in LR and some LR parameters and whatever type of CV technique that you want to use, and then you fit it, and then you will have the best parameters and the best score that was achieved given whatever metric that you chose to evaluate with. What's interesting here, if you all would humor me, what's interesting here is that I want to know what metric was used to evaluate grid search CV. Does anybody know the answer to that question before I ask it to ChatGPT? Okay, so because the example did not specify, I'm going to just put in grid search CV and go to the same page I was telling you about before, and then I'm going to go to scoring. A strategy to evaluate the performance of cross-validated model on the test set. And so you would have to look through and figure out, what the scoring was going to be, right? And so it's going to go to whatever the default is for that particular type of problem. So these are all examples, so depending, there's going to be a default one for classification and a default one for regression. I imagine it's probably accuracy. Yeah, just like I said, accuracy. And then it explains what accuracy is. But had this been a regression, if you had used the support vector regressor, it probably would have chosen like mean absolute error or mean squared error to evaluate. And now it's showing you, hey, you can use the scoring parameter to influence this and change what metrics that is used to evaluate. You can also pass in a list, which I do quite commonly. So you can say, I want to do a grid search, but I want to evaluate this on accuracy, precision, and recall. And you put it in a list. And that works very well as well. So yeah, that's a gentle introduction to support vector machines, optimal separating hyperplanes, and machine learning in general. I'm going to take a break from this ChatGPT for a minute so we can go through notebook number 4. We can get on and play with it a little bit more later, but I do want to make sure I cover the introductory material, for logistic regression and the support vector machine examples and gradient optimization. So there's a lot of helper functions in Sklearn. This is an example of one called cross-val score, right? So the way this works is, remember up here, we created this logistic regression object, and we named it LRCLF for logistic regression classifier, right? So we can use cross-val score. We pass in our estimator, whatever that is. It could be SVM, right? It could be just whatever estimator we create. Our training data, the targets, and then we pass in our cross-validation object. So remember, previously we created our CV object right here. It is a 3-fold shuffle split, right? So this is a helper function because we passed in an estimator, we passed in some training data, and we passed in a cross-validation object, which is a 3-fold shuffle split. And cross-val score performed 3-fold cross-validation and spat out for us 3 different accuracies. So note, all this code that we ran up here could be replaced with one line, right? So there's another one that I think is very useful, and we will jump over here. So this is another all-in-one helper function. and we'll see what ChatGPT comes up for us. So looks like they're sticking with support vector machines since we asked about that earlier, which is nice. Iris data set once again, which we loaded up, right? Here we're creating the SVC object with a radial basis kernel, a cost of 1, and a gamma of 1. And then what are we doing? Well, we're passing in one line. We use cross-validate from sklearn.model selection. And we pass in the SVC object that we created. We pass in X and Y. We say, hey, we want you to do 5-fold cross-validation, and we want you to return us the accuracy and the F1 micro average, right? And we can talk about that as well. That's an interesting one. So in this example, cross-validate function is used to perform 5-fold cross-validation on an SVM classifier. The model is evaluated using 2 scoring metrics, accuracy and F1 score with micro averaging, right? The mean accuracy and the mean F1 score across the folds are then printed. Note that cross-validate returns a dictionary of arrays where each array contains the scores for each fold of the cross-validation. The mean of these arrays is used to estimate the performance of the model, right? So this will perform in one line of code 10-fold cross-validation for you, right? And so it's very useful. It can save you a lot of time. I think it's great, but I also think that you should remember, you should understand what's going on behind the scenes, right? It's important to know, for example, this is using the default cross-validator for cross-validate. So if we look that up real quick, we will see CV. Default. None is to use the default 5-fold cross-validation. It to specify the number of folds, okay, in a stratified k-fold. So if I'm reading this correctly, because they entered in the number 5, you should be doing a stratified k-fold cross-validation 5 times. So let's talk about that. Does anybody know what a stratified cross-validator does, or how it's different?
Roughly speaking, like if you have male and female as 2 categories, it would cross-validate. It would split the data set up into male and female, cross-validate for male, cross-validate for female, if I'm not mistaken.
Yeah, that's pretty correct. I would say when it selects its folds, it's going to make sure that male and female are proportionately represented in each one of the folds. So it's still a random selection, but say your data set is split 60-40 male-female, it will try to enforce those general splits in proportionately in the thing that it returns. It's not like you say, well, I don't really see like what the huge advantages of that, and maybe there's not a huge advantage in a 2-class problem. But for example, let's say there's an example at the bottom of notebook 4 where you have this really complicated problem of predicting plankton in the ocean, right? In that instance, there's 131 different types of plankton. That means that's 131 class problem. Holy smokes, that's a complicated problem. Why is that complicated? Well, if you're predicting male and female, that's a 2-class problem. So this is really rough general rule of thumb, but it works. You say, okay, how hard is this problem? Well, if I was going to guess male, female, I got a 50-50 shot, right? If I build a classifier to do my guess for me, it should be better than chance, right? It's got to be better than 50% or it's not a good classifier. So you can kind of gauge the toughness of your machine learning problem. If you have to predict 131 different types of plankton, then you've got a 1/131 problem. And that's way less. The average accuracy is way less than 50%. It's 1/131. So you can kind of adjust your expectations for how well is this machine learning algorithm going to do. I guarantee you that a two-class problem is going to have a much higher average accuracy prediction than a 131 class problem. right? And so the thing that you'll run into as well is when you do cross validation on a data set like that, where you have a multi-class problem, you need to guarantee that the test and the training folds that you randomly select have at least 131 classes in each fold. And a lot of time these classes will be underrepresented, right? So if you have a class that only has like 10 training examples and you're doing just straight random selection, it's very, very high chance that you will end up with a random selection that doesn't include any instances from that particular class. And so you use the stratified cross-validation to make sure that you have all of your classes represented in each fold and that they're proportional and so on and so forth. It's very helpful. Okay,